Welcome to video 4.2 in our first Principles of Astrophotography series. In this video, we discuss dispersion. That is, the wavelength dependence of the speed of light in a medium such as air or glass.
Why?
Good question. Because dispersion causes chromatic aberration, which afflicts all refractors. It's the reason why our Cat 91 has 5 lens elements in it, is to correct for that chromatic aberration. And if you don't account for dispersion in air, you target the wrong wavelengths with your narrowband filters. So it is important for that too.
Yeah. Okay, but what happens when fog disperses in LA, California?
I can see clearly now, the rain has gone.
Blah. You see LA.
Thanks for that.
You're welcome. I'm Ren Edwards.
And I'm Boyd Edwards.
Let's talk sensor sensibility. All right, principle 48, dispersion. Dispersion is the wavelength dependence of the speed of light in a medium.
Yes. So light travels at speed c in a vacuum, which is 3 times 10 to the 8th meters per second. It has wavelength in vacuum that's dependent on its frequency. When it enters a medium, it travels at a slower speed, b. And the wavelength of the light in that medium is going to be less. But the interesting thing is that wavelength depends on the amount of dispersion, and the speed of the light through that medium depends on the actual wavelength. So it's kind of complicated.
Principle 49, refractive index. The refractive index, N equals C over V of a medium, is the speed C of light in vacuum divided by the speed of light V in the medium.
Okay, like we talked about before, we have speed C in vacuum, which is 3 times 10 to the 8th meter per second. Speed V of light, measured in meters per second, but something less than this original speed. The refractive index is defined as the ratio of those two speeds. So this is the speed in vacuum divided by the speed in the medium, such as glass.
Principle 50, reduced wavelength. The reduced wavelength lambda prime equals lambda over n of light in a medium is a ratio of the wavelength lambda of this light in vacuum and the index of refraction n of the medium.
So we're just saying the same thing in equation and in words. So lambda prime, that's this wavelength of the light in the medium, equals the wavelength of the light in vacuum divided by the speed of light. So
N.
Divided by n. Thank you for that. Divided by n. So if you take that wavelength, let's say the wavelength in vacuum is 1 meter, and you divide by the index of refraction. I think I need to say one more thing about the index of refraction. This index of refraction is a number that is greater than or equal to 1. Why is that? If the medium is vacuum, then the speed in the medium is this. The speed in the medium is exactly the same as the speed in vacuum. And then you take C divided by V, but they're both the same, and you get 1 for the index of refraction. But if the speed in the medium is 1/2 of the speed of light in vacuum, then you're going to say N is C divided by 1/2 of C. You're dividing by a fraction, you invert and multiply, and the C's cancel, and you get the index of refraction is 2. So you're always refractive indices or indices of refraction are always greater than or equal to 1. So the same thing happens over here. If this index of refraction is greater than 1, then you're going to be dividing that wavelength by something that's greater than 1, which will give you something that's less than that wavelength. So you're going to reduce the wavelength. So lambda prime will always be less than or perhaps equal to the wavelength. I'd like to just show you a quick derivation. It's a really simple derivation, but it tells you something about light when it enters a medium. And the important key for this derivation of this equation is to note that when that wave enters the medium, comes into the glass or the water, the oscillation frequency is going to be the same in the medium as in the vacuum. To assume otherwise would mean that at the interface between the glass and the vacuum, that somehow it'd be getting off kilter, but it can't. The only way it can propagate into the middle, into that medium, is for the frequency to remain the same.
Right.
So if we can write C equals nu times lambda in vacuum, we can also write the speed of light in the medium as nu with the same frequency nu times lambda prime. So this is in the medium. And if we divide these two equations by each other, so I'm just going to put a line like that, divide the left sides of these two equations, and then divide the right sides. So the left side will be C divided by V is lambda over lambda prime. But C over V is something that we just talked about. The refractive index. This is just the refractive index. So N equals lambda over lambda prime. And if we want to solve that equation for lambda prime, we're going to multiply both sides by lambda prime, and divide both sides by N, which gives so you wanted some math. I gave you some math.
I didn't ask for it.
Oh, you didn't? Okay, fine. The application of this is quite important. When you look you have an object that's on the bottom of a pool of water, for example, its apparent depth will be less than its actual depth. So you're going to grab from outside the water, you're going to grab for that object, and I don't know if you've ever done this. You grab for the object, when it isn't there, it's just still water. You have to grab deeper than you think, and that's because of this principle here. This principle also is important. The idea of dispersion is important in the creation of rainbows. The fact that that the speed of light depends on the wavelength is the reason why we have rainbows in the sky. Thanks for watching.
And we'll see you next time.